Our next speaker is Sjanne, and she'll be talking about optimization of eigenvalue bounds for the independence and chromatic number of graph powers.
Yes, thank you. Yes, my name is Sjanne, and I'm from the University of Eindhoven. And I want to talk about some joint work with my supervisor, Aida Abiat, and also Gabriel Coutinho, Michelangelo Fiol, and Bruno Nogueira. So I briefly want to talk about spectral bounds for the independence number in general in the literature and give some background on the problem. And then we'll look at two new bounds in two different scenarios. So as the title of this talk suggests, we will be looking at the spectrum of a graph, and we use two different notations for this. So if we mean each and every eigenvalue, we just put them as lambda in non-increasing order. And if we mean all the distinct ones, then we say theta and put a superscript for multiplicities. And we're interested in the spectrum of a so-called power of a graph. So we say that the kth power of a graph is the graph where we connect vertices when their power or their distance is at most k. So for k is 1, we just take a graph. And for k is 2, we get all these extra edges at distance 2. And same for distance 3, etc. And here you see that the diameter is 4. So if we do this once more, we just get the complete graph. And for these graphs, we can also generalize the independence number. So the k independence number is the maximum size of a vertex set where the pairwise distance is greater than k. And for k is 1, that just means we have the independence number. So vertices cannot be neighbors. But for k is 2, for example, in this 8th cycle, you see that you can only select 2 vertices. And it's easier to see if you note that the k independence number is really just the independence number of the kth graph power. And in the same way, we can also generalize the chromatic number. So for the k-chromatic number, vertices that are at distance at most k cannot receive the same color. And there's this one inequality which relates to two quantities. So the chromatic number is at least the number of vertices divided by the independence number. And if we just put this kth graph power instead of g, we see that this also holds for the k-chromatic number. So our goal is to extend and optimize certain eigenvalue bounds for the normal independence number to this k independence number. And by the equation on the previous slide, that also gives us a lower bound for the k-chromatic number. So part of our motivation is that the problem, like the normal independence number, is NP complete. And this is actually still the case for some very specific graphs. But these eigenvalues can be computed in polynomial time with Gaussian elimination. So these are very good candidates for this kind of upper bounding. And another problem is that perhaps the most straightforward generalization of eigenvalue bounds for the independence number doesn't really work as intended. So theoretically, what we could do is take an upper bound on the independence number and apply it to this kth graph power. So by definition, that gives an upper bound on the k independence number. However, we don't know in general anything about the spectrum of a kth graph power. So given the graph itself, we cannot say anything about this. And what we want, therefore, is to have an upper bound that only depends on the spectrum of the graph itself. So this k-independence number is important in different areas of mathematics. For example, in coding theory, we can see a code as a k-independent set in a Hamming graph. But there's also something called this quantum k-independence number. So in quantum theory, we have, similar to graph theory, an independence number, and you can also generalize this to the quantum k-independence number. And for this, it's not even known whether this is a computable function in general. And some of the upper bounds that we present here are actually also an upper bound for this quantum k-independence number. And finally, it also relates to certain other graph parameters. So for example, the average distance can be lower bounded by this k-independence number. Now, our main tool to prove bounds like this is interlacing. So given a sequence of lambdas and a shorter sequence of mu's, we say that they interlace if these equalities hold for every index. So if we put this visually, then for each mu, we have this pair of lambdas where it has to be somewhere in between. And in our case, we want to apply this to graphs. So we have this symmetric adjacency matrix and its eigenvalues. And one particular case where we know that interlacing occurs is when we take a principal submatrix. So in terms of the graph, if we take an induced subgraph, then its eigenvalues always interlace that of the original graph. And we call this Cauchy interlacing. So before we apply this, I just want to show some previous results in this area. And there's actually two very important bounds. So one is the inertia bound by Svetkovic. And it states that the number of non-negative and the number of non-positive eigenvalues, they always upper bound the independence number of a graph. And the second one that is often used, that will also be generalizing, is the ratio bound by Hofmann. And this bound only holds for regular graphs, but if the graph is regular, then this eigenvalue expression also always upper bounds the independence number. And this bound also comes with a nice condition for equality. Now this bound relates to another graph parameter that you may have seen. So the Laplace theta number is actually in between this alpha and the Hofmann bound. So this is also an upper bound for the independence number. However, this Hofmann bound is much easier to compute, as you can see, whereas the theta number requires semi-definite programming. Now, I'm not going to go through these all, but just if you're interested, here are some other papers that have studied this k-independence number. And one that's particularly important for us is this one by Fiol. So he came up with the first bound based on eigenvalues of a graph. Now, our idea of applying optimization in this area is not entirely new. So I mentioned before this Laplace theta bound. This requires semi-definite programming. But there's also another very famous bound by Delsart. So this was found in relation to some coding theory problem. But this is a bound that uses linear programming. But it only holds for a certain graph family. And then recently in 2019, Fiol came up with a generalization of this Hofmann bound. And he used linear programming to get good upper bounds for specific graphs. So our idea was to take its counterpart, this inertia bound, and to see if we can do something similar. So this is part of a series of 3 papers. It started in 2016, and a few new bounds on this k-independence number were found. And they all had this, this term of an eigenvalue to the power k. So the idea was maybe we can generalize this to some kind of polynomial. And this is the case. So these bounds have been extended to contain some polynomial on the eigenvalues of degree k, which we are basically free to choose. And so the last logical step was to optimize this and to see which polynomial gives a good bound for specific graphs. So before I get into this, I want to very quickly look at a special case of this problem, when there is actually a relation between the spectrum of the graph and the power graph. And in particular, we looked at an old question from Alon and Mohar. So they wondered, if we fix the girth and the maximum degree of a graph, what is the largest possible value of this k-chromatic number that we can still achieve? Now for KS1, this problem was already posed by Weising, and it was solved using the probabilistic method. And in the meantime, the case KS2 has also been settled. But for KS3 and larger, this problem is still open. So in a partial attempt to answer this, we looked at an old paper from Fiol. And here he defines something called the predistance polynomials. So what they exactly look like is not important here. But the idea is that we define some inner products on the eigenvalues of this graph. And we have a sequence of polynomials that are orthogonal with respect to this product. And we normalize them with regard to the largest eigenvalue of the graph. And what Fiol showed is that if we take the sum of such polynomials and evaluate it on the largest eigenvalue, then we have an upper bound for this. And this upper bound contains a parameter that he called as k, which is essentially the number of vertices at distance at most k from a vertex. So you can see here the relation to coloring in the sense that these would be exactly the vertices that you're not allowed to give the same color. And this bound has equality whenever this relation holds. So whenever the adjacency matrix of this kth power graph is polynomial in the original adjacency matrix. So what we can see is that we have equality here exactly when there's a relation between the two spectra. So exploiting this, we can get a lower bound on the k-chromatic number. So whenever we have equality for this lemma, we can get this first type of bound, which looks very much like this Svetkovich bound that I showed. And we can also derive a second bound, which is of a different type, as you see here. Now, this inner product that I showed you looks quite complicated to compute, but there's actually a case where this can be done much easier. So in particular, if our graph is regular, and we say that k is the girth minus 1 divided by 2, in that case, we know that the graph is k partially distance regular. And what that means for us in particular is that this polynomial is easy to compute with a recursive function. So in this specific case, we can very easily compute our bounds, and we did this for several graphs in Sage. Now, later in this talk, I also mentioned the k-independence number, so we just translated it back to this number so that it's clear what the relation is. But you can see that for quite a few of these graphs, we find exactly the k-independence number with this bound already. And another tight example we can find if we look at a paper by Kang and PLO with relation to this question by Lon and Mohar. So what they did is they defined a graph product on that bipartite graphs, which they call the balanced bipartite product. And if we apply this to some very simple graphs already, we get tight examples. So for example, if we take even cycles of length 8 or length 12, we see that we get exactly the k-independence number. Now, in general, there is no relation between the graph spectrum and that of its powers. So then we have to do something slightly different. So if we have an adjacency matrix and a polynomial of degree k, we say that W is the minimum diagonal entry of P of A. And we also do the same for the maximum entry. And in that case, we can get the following inertia type bounds as an upper bound for this k-independence number. So as you can see here, this is very similar to Svetkovich bounds, except that we have this polynomial on either side now. Now I was going to prove this, but I see that I'm running very short on time. But just to give you an idea, this independent set we could see as a block in this matrix P of A, and this is a principal submatrix. So basically what is happening here is we can apply Cauchy interlacing, and this gives us exactly this first term of the bound from the previous slide. And you can also do this for the larger term. So before we apply linear optimization to this, it's always good to ask ourselves, of course, is this linear? And if we simplify the bound a bit, this is much easier to see. So for example, we may assume that only this first term of the minimum is there, because we can just flip the sign if we take the negative of this polynomial. And in a similar way, we can translate it and assume that this W is just 0. And the idea is now that for each vertex of the graph, we create this integer program. So for each vertex, we assume that it corresponds to the smallest diagonal entry of PA. So like I said, we can assume this to be 0. And then we have a second constraint, which says that the other diagonal entries should be at least as large. And the way we compute our bound is we have this characteristic vector B, which is set to 1 exactly when this equation is satisfied. So exactly when P on an eigenvalue is larger or equal to 0. So of course, this takes a little bit more time if you have to run this program for every single vertex. However, the nice thing about this is that we don't require any type of walk regularity here. like for example, Veal's optimization bound. And if we look at small graphs that are not regular, we see that actually for the 2 independence number, in quite a large percentage of the cases, we still get a tight answer. So we also compare this for all the named graphs in Sage to this previous bound from 2019. And sadly, we are sometimes outperformed, as you can see. But there's also certain graphs for which we do better, for example, this Meredith graph. And we were able to fill in some of the gaps of the irregular graphs here. For the sake of time, I'm not discussing this here, but in our paper, we actually have a second mixed integer program, which is actually much better than this. So if you're interested, you can also see how that compares to this 2019 bound. And actually, in certain nice cases, we can also make it a little bit faster. So whenever our graph is k-partially walk regular, which is the same assumption as Veal makes, we have a constant diagonal. So in that case, we could just scratch the first 2 conditions, and we only have to assume that the diagonal is 0. So then we only have to solve this once. So one case where this happens, for example, is in the prism graphs. You can see some of them here. So these are Cayley graphs of the dihedral group, and these are walk regular for any k. And as long as we don't have n is 2 mod 4, we see that our mixed integer program always gives a tight answer. So here is an infinite family for which this bound is tight. And another one can be found in the family of odd graphs. So these are basically a special type of Miser graphs. You can see the most famous one here, O3, which is basically just a Peterson graph. And we can show that this mixed integer program for our bound, it always gives the answer 2l minus 2 for odd L and 2l minus 1 for even L. And for all small graphs where we can experimentally check this is always tight, unless we pick O5 for some reason. So probably this is another family for which this bound is tight. So I want to just close this off with some open problems related to these bounds. One thing that you may have noticed is that this mixed integer program is quite straightforward. So what we could do is try and refine this to make it a little bit faster, which would allow us to test larger families of graphs. And in general, it would be good to look for more families for which this is tight, especially in the context where the del start bound does not apply. Since this bound is basically, it's very good and it's very fast, so we don't really try to compete with this. But it's also quite restrictive. So there's this huge area where this bound does not apply and a lot of improvement might be possible. One thing that was particularly interesting, what we saw when we were testing for these graphs, is that for the odd graphs, all the optimal polynomials that we found, they converge towards these minor polynomials that Veal used for his optimization. So in general, these 2 types of bounds are thought to be not connected in any way. But this gave us the idea that perhaps there is something going on there. So it would be interesting to see if this is something that's there for graphs in general, or maybe that for odd graphs or specific families, this is just a lucky coincidence. And finally, like I mentioned, there's many connections to other fields. So for example, if we can improve these upper bounds on alpha k, we could also use this to show that certain kinds of codes cannot exist. So that's all I wanted to talk about today. Thank you all for watching. Are there any questions?
Yeah, let's thanks, Sjanne. And we just have a minute here, but does anyone have a really quick question? Sounds like we don't have any questions. So let's thank Sjanne one more time.